Okay, I think that we can start because a long time ago I received the feedback that most difficult time to have a presentation is just before lunch. The reason for it, and when you are late or going over the time, you will receive the bad feedback because the people will come late on the lunch, they will not have a proper food and so on. So I want to be sure that you will get your lunch. And as always, I have very, very heavy slides. Yeah, so who attended my sessions sometimes before, you know that my slides are heavy, so I'm trying to give you a lot of information all the time. So we have 2 hours. If you will stay all the time with me, I promise that I will really show you what we are doing in both transport as well as the services. And we will go also over the details. So it's really like a technical presentation, I can promise. So, okay, I think that everyone is in the room. So my name is Jiří Chaloupka. I'm technical marketing engineer, responsible for EVPN and segment routing in our service provider organization. So mainly iOS XR and service provider platforms. So I will go immediately to the agenda because I wanted to show up like all the time, like what we are basically doing, what we will cover, why we believe that segment routing transport makes sense in service provider environment, how exactly we are deploying. We will also like go over the basic things of the segment routing to explain how segment routing works, because I think that it's really important to understand these things. Then we can go to the more advanced topics. We will show how to do the fast reroute, how to do the traffic engineering, how to basically do the design of the interdomain LSP and so on. And we will also go over the part which is covering the services, because you will see that the transport and the services together are like a brother and sister, because what we want to do when we are moving to the new term like intent-based networking, we want to be sure that everything what will be like SLA request from the services will be properly programmed to the network, will be properly programmed to the transport, and all the stuff will work together. So we will go over all these parts, and hopefully we will make it in the 2 hours. So this picture is a very old one. If you saw it before, you probably implemented or used the unified MPLS. Cisco had a huge success with this design. This design is very stable, it's very robust. One drawback of this design is it's pretty complex. If you will implement everything from the unified MPLS, you need to have expertise in multiple areas, but in the end of the day, it's still valid design. We really using this in the multiple networks, and it's really very stable. On this slide, I will show how basically we are developing or how we are evolving the existing unified MPLS design to something what we call EVPN 5.0, like some time ago, and something what we call the Metro fabric. You can see that the main part of the evolution is the simplification. First, when we look at the blue part, this is like mainly intra-domain transport. We are trying to simplify the current protocol. So basically, when you look at it, everyone is running some IGP. Most of the time, and when you are using the Cisco, you are running the LDP for the intra-domain LSP, and then you are running some of you is running RSVP for fast reroute, mainly for fast reroute. Honestly, we don't have too much customers for the traffic engineering because it's quite complex. We will talk about it a little bit more, how we can make it much easier. And then when we look at the interdomain LSP, we have a BGP-LU, and on the services, again, LDP, typically for point-to-point services, or L2 multi-point services, and BGP for traditional L3 VPN services. This is something like whole the basically protocol stack which you are theoretically running in your network. The first simplification when we did, and we will go over the details, I can promise, is that we're basically using the IGP with the segment routing extension, and with this one, we can remove LDP and RSVP. So this is like a first step. Then we can also use the segment routing to remove the BGP-LU for interdomain LSP, and we will also go over like the details how we can do it. Because it's not enough, we can still simplify more. So we also decided to put together the certain stuff for the services, and we can remove the LDP also from the services side, because we can use the BGP as a unified control plane for all the services across the network. And you will see that it's not just for a service provider network. We can then use the BGP over the data center, SP data center, next generation CO, whatever you will call any part of the network. So let's first let's really focus on the segment routing, like really basic things, how segment routing works, because I believe that when you will understand this and everyone will be on the same page, it will be much easier to understand the more advanced stuff. So first, why segment routing? First, we can remove the LDP. I believe that everyone who configured the LDP and IGP had a problem with LDP IGP sync. You know, most of us tried something and had a problem with it. So you will get rid of this small thing. Another thing what I'm saying that is coming almost for free is a fast reroute. Topology independent LFA is something really for free. Simple configuration, natural part of the segment routing, and we will go over the details. So we can theoretically claim up to 50 milliseconds protection time. This is something what everyone is taking, up to 50 milliseconds, like a fast reroute. We can cover 100% of the network topologies with this TI-LFA, topology independent LFA. We will also touch this topic, why we were not able, for example, with the LFA and remote LFA, we were not able to cover all the network topologies. On the opposite side, when you look at it, we are using like different control plane. And our first implementation of the segment routing is with the MPLS data plane. We also talk about how we can have IPv6 data plane, but the MPLS data plane is right now the current one. So we are using still same data planes. When you look at what the ASIC or what the NPU has to do, is still completely the same. Impose the label, swap the labels. I'm just using the different control plane. Instead of instead of LDP, I'm using the IGP. Very easy segment routing, traffic engineering. We will go over the details. And segment routing was actually well adopted with not just in the service provider environment. We have also huge success with the web OTT. So basically, we can also say that we are moving also to the let's say data center part of the network. So when we look at this picture, we will go first. We will go over the simple IGP domain to explain how segment routing works. But you can see from the data plane point of view, I already talked about it. We have MPLS. This is main part of this presentation will be about MPLS because this is an actual thing what you can do today. The next part is the IPv6 data plane. We will touch it. We will explain that it's not something like LDPv6. It's a completely different thing. We will touch this part. And for control plane, we are using the existing protocols. Again, it's an extension of the ISIS or OSPF. And this is the important part. From the troubleshooting point of view, from the deployment point of view, we are not bringing another control plane. It's existing control plane with some enhancements there. And from the computation part, you can have a dynamic or the static expression of the path. So let's go very quickly over the quick overview how segment routing works. Let's really compare it with the LDP. So in this case, when I have a router 5 will have loopback 1115/32, and when I will use the LDP, what will happen? I will allocate my label for my loopback. I will advertise the label to router 2, to router 4. These guys will, again, allocate own local label from the LDP and will advertise it somewhere else. What I'm doing here with the segment routing, together with the loopback, as an operator, I'm also responsible to configure something what we call prefix-it or node segment. This is something what is like the static configuration, like loopback, for example. So in this case, I decided that I will have my local value for my local label for my node SID. It will be 16,005. It's again MPLS label. It's just MPLS label for data plane, nothing else. If you will take the Cisco device, typically you will use the range from 16,000 to 23,999 is by default. This is something what we call segment routing global block. You can configure it, you can change it, but on all the pictures when you will see something starting 16,000, it's typically like the segment routing range. Yeah, this is by default what we are using. So right now with the IGP, I will take the 1115/32 and I will advertise it together with this, prefix it, together with this segment. So I don't need any LDP additionally to advertise me this label. So I'm getting this information on router 2 and router 4 together with the prefix, right? What will happen, router 2 and router 4 will use as a local label completely the same one. Again, they will use a 1605, and they will advertise it somewhere, they will advertise it to the other neighbors, right? Because everyone is in the same IGP domain. So it means that everyone will use the label 1605 when want to send something to router 5. It means that this label, this prefix set, is actually global right now. So I have a global label for whole IGP domain. So I must be sure that on the router 1, router 2, 3, 4, I will also configure the unique prefix it, unique label for this one. So for example, on the router 4, I will have 1604. Then when we look at like how this works, let's say that, for example, I want to send something to router 4. Router 4, I configure this prefix set 1604. When router 1 wants to send something to router 4, what will happen? I will have traditional ECMP, so I will be able to balance over the router 2 and 3 to router 4. Completely same I was doing before with the LDP. So all the principles like the ECMP and this stuff from the data plane point of view, it's a completely same. Then there is one more very important part of the segment routing, and this is a very, very different. Automatically, when you will enable the segment routing, the router will also allocate something what we call adjacency segment for each link which is connected to the router. And this is coming from the dynamic range. So you can see in this case, I'm starting from the 24,000 something. This adjacency segment is the unique for the node. So it means that I don't need to have any specific set for each link in the network. Basically, each node is allocating dynamically this particular adjacency segment. And later on, I will show you how we are using it. So imagine that in this case, I want to, and let's not think how, basically I will compute this path, but let's say that I want to send the packet from router 1 to router 5. I don't care how the packet will go over the network, but I want to be sure that I will always use the link between 4 and 5. So what I will do, I will basically say, okay, I will use the node set of the router 4, so I will impose the label 1604, and additional label will be the label of the link allocated by router 4 for the link between 4 and 5. So basically, I'm able to stack the labels, like use the node set, I'm able to use the adjacency set, and basically stack it and create something what basically we call traffic engineering. Later on, I will talk about more the details, but this is exactly what we are doing for segment routing traffic engineering. Basically, we are stacking the node sets, adjacency set, and you can combine it how you want to do it. It doesn't matter how. Basically, you can have like node set, adjacency, another node set. There is no limitation. When you will think about it, how this works, it's a source routing. Basically, router 1 right now is doing the decision how the packet will go over the network. No one else is involved in the decision. You don't need to signal that you basically created the traffic engineering over the router 2 or 3. Like before, you need to RSVP and you need to signal that you will have certain tunnel, right? Here, on the router 1, you just send the packet, and what will happen is that router 2 and 3, they will do the PHP. The top level will be adjacency set. This adjacency set will be forward based on the information on the router 4. It means, again, I will do the PHP and I will send it to router 5. Normal swapping, popping operations, how I'm doing with the MPLS today. And this is exactly what I just described. So when I will have a payload, I will go to router 1. Router 1 will impose, for example, 1604. On router 2, I will do the swapping. The swapping will be between 1604 to 1604. Then going on router 3. Router 3 will do the POP operation and will send the payload to the router 4. So just a quick reminder, what I have two important things in the segment routing IGP. I have a node set, the prefix set, the green one, which is allocated per node, and then I have an adjacency set. This adjacency set is of per particle link, and it's very important. Later, once we will go to the fast reroute, you will understand why we need to have this adjacency segment here. Now, I don't like too much configuration on the slides here, but I want to just show you how difficult it is to basically enable the segment routing in your network. Who likes the ISIS will look at the left side, who likes more OSPF will look at the right side. But basically here, you can see that it's very, very simple. You just go, you will just enable your address family, for example, for ISIS. You will enable segment routing MPLS. And under the loopback, you will specify the prefix set index. when I configure the index, it means I'm starting from the range 16,000, so I will allocate the prefix 16,001. When I will have index 2, it will be 16,002, and so on. So it's very, very simple configuration. So with this one, we are able to get rid of the LDP. So we have like very easy way inside one IGP domain. We have a segment routing as an extension of ISIS or OSPF. Okay, so let's look at how we can do the fast route. And now it's very exciting because we will combine the node SID and adjacency SID together, and you will see that you as an operator, you don't have to configure anything. Basically, everything will happen independently because each node in the IGP domain knows the network topology, right? So everyone can compute the backup path independently without any extra configuration. So let me first say what is the LFA, loop-free alternate. It's a very smart idea where I will basically calculate my primary path for a certain prefix, and then I say, okay, primary path is going over the link 1, and what will happen when the link 1 goes down? So I will pretend that link 1 doesn't exist, and I will compute one more time the shortest path. So basically, I will get my backup path. So what I will do, I will install this backup path to my hardware, and in case of a failure, I will just switch pointer in my hardware, and I will start to forward. So basically, I pre-computed my backup path, and I know I need basically detect the failure, and immediately I'm able to switch to my backup path. The problem of this is that it works in the certain topologies. When I will have a ring, I can have a problem because I will detect the failure, I will send it to my neighbor, but my neighbor didn't have enough time to get information about any failure, and will send it back to me, right? So then we created something what we could call a remote LFA. But remote LFA has also some limitations, and now we will go over all of this with the topology independent LFA. So first, easiest use case is something what we call zero segment topology independent LFA. In this case, we will all the time send the traffic between node A and Z. And the primary path is A, 1, 2, and Z. This is always a primary path. So let's say that I'm sending the packets from the A, so I will impose the prefix SID of Z, because it's one IGP domain. I know prefix SID of Z. I got it from IGP. Everyone knows it in the IGP domain. So it's go from 1, 2, and Z. Perfect. Now, I will break the link between 1 and 2. What will happen? In this case, what I will pre-program is that I will just have a different outgoing interface. So basically, what will happen on router 1 will still keep the same packet, prefix SID of Z, original packet, and will just send it to router 5, 4, 3, 2, and Z. Easiest use case. But now the problem is that in this case, when the router 5, for router 5, when the primary path to Z will be over 1, 2, and Z, I have a trouble, right? Because when the router 1 detect the failure between 1 and 2, will send it to 5. But for 5, the primary path is over 1. Router 5 will send it back. I will have a local loop, TTL will expire, but I will have a black hole link. So this is something what we call single segment TILFA, because I'm looking for the node which will forward to router Z, but will not forward over the router 1. We're calling this like a PQ node. In this example, let's say that the router 4 is a node where the primary path to Z is over router 3, 2, and Z. So even if router 4 doesn't know about any failure, all the time to router Z will forward over 3, 2, and Z. In this case, what I will pre-compute is a path that I know that I have to impose additional SID, additional prefix segment, which will identify the router 4. So basically what will happen here, when the failure is, when I will detect the failure on the link between 1 and 2, I will impose the prefix SID of the 4, then I will keep the prefix SID of Z and original packet. So what will happen from the data plane point of view? Router 5 will do the PHP. So the top label which arrive on router 4 will be prefix SID of Z. Router 4 doesn't know about any failure right now. So router 4 will just send it to router 3, 2 will do the PHP and will send it to Z. So what is the nice part of this? That again, I did the local decision on the router 1. In this case, when I want to protect the link between 1 and 2, when router 1 will be only one router in the network who is supporting TILFA, I'm able to do it. No one else has any clue that I'm doing any TILFA. I don't need to signal anything. It's my local decision. And the nice part of this one is also very easy to troubleshoot. You can go to your LFIP, your FIP, and you can immediately see what will be your primary path, what will be your backup path, what are actually your node sits which you will impose. And again, because your node sits are the global, unique in your IGP domain, most probably you will also know which node sit is mapped to the which node, right? So it's very, very easy to troubleshoot. Okay, let's take one more example where it's even more complicated. And this is a use case where even a remote LFA doesn't work, and we really need to use the topology-independent LFA, and we will use all the beauties of the segment routing to go over this use case. Let's assume that I have a link between a router 4 and 3, really high cost. It's some T1, E1 interface, and I want to be sure that I will use this link just in case of any failure. Normally, I don't want to use this link anymore. So basically, even the forwarding between 4 and 3 will be over 5, 1, 2, 3. So normally, no one is forwarding over this link. I'm in trouble. Because when I will use the previous logic, what will happen? Router 1 will send it to router 4. Okay, router 4 will, but router 4, when it goes to router 3, wants to go over the 1, right? Okay, so let's take one more node. So okay, let's send it to router 3. But to router 3, my primary path is going over the link which I'm trying to protect. So previous solution completely doesn't work in this case. So what I have to use here is something what we call the double segment TI-LFA, and I'm actually using the adjacency segment here. Because adjacency segment, if you remember, is here for particular link. I allocated this label for the link. So it means, for me, the cross connect. So in this case, router 1 will impose, again, the prefix sit of 4, but will also impose the adjacency sit of the link between 4 and 3. So when we look at from the data plane point of view, the packet will arrive on router 4. What will be top label on router 4? It will be already the adjacency segment of the link between 4 and 3, because 5 will do the PHP. What will do the router 4, because router 4 allocated this adjacency sit for this particular link, will do the PHP of this adjacency sit, will do the cross connect and send it to 3. And 3 will see the top label, prefix it of Z. Again, do I need to signal something in the network? No. It's all this information I have locally on router 1 from the IGP. I did my local decision on the router 1. Yes, please.
So the case where the P and Q space have no intersection, right?
Yes.
This is your example now. And that means for router 1 and for router 4A, actually to calculate, it's separated?
No, the question how is it calculated? Router A is not calculating anything. Router 8 is still sending the original packet, because router A doesn't know about the failure between 1 and 2.
Router 1 has to calculate.
Yes.
Calculate the router, actually. And so it has to calculate this. First run is router 5 won't do it.
No,
Router 4 wouldn't do it any also.
Because from
3 is doing it. You will forward to 2.
No, the logic how you will look at this one. You know all the network topology. So you know from the one, okay, when I will send the packet to router 4, what will happen? Router 4, because I know the network topology, will send back to me. Okay, I don't want to do this. If I will send it to router 3, actually my primary path to router 3 is over the link which I want to protect, right? So I look at it and say, okay, when I will force the router 4 to do the cross connect between 4 and 3, this will work. And this is exactly the logic how I will construct the label stack. It's just the algorithm how I'm using the topology.
Before you have to conclude that the P and Q space are separate.
Yeah, exactly. You will make the conclusion basically again from the topology. Exactly. There's no you said it right. There is no PQ router. Basically, P and Q is separated now. So now for this one, if I want to have a TI-LFA, what I have to configure, I just, again, in ISIS or SPF, I go and I will just enable the TI-LFA for the particular link. Again, all these things happen automatically. You don't have to go, you don't have to pre-configure some tunnels or backup paths or something like this. This is something what is happening on each router independently, because each router has this topology database. And that's a very nice part of it. Okay, so how I said, the RSVP is most of the time used for fast reroute. So we find out the way how to do it with the segment routing without RSVP. But to be fair, we still didn't cover the traffic steering. Still, someone is using the RSVP for the traffic steering. So let's look at this one more time. This slide, first I mentioned that basically this is a traffic engineering, stacking of the sets, basically stacking of the labels. This is a whole idea. So when I will make it like a little bit more difficult, and I will say, okay, this is, I want to first forward to router 3, then I want to forward to router 4, and then I want to do the cross connect. This is something what we call creating the SR policy, segment routing traffic engineering policy. And each segment routing traffic engineering policy has a certain SID list to forward the traffic over the IGP domain. So in this case, I wanted to be sure that I will forward traffic always to router 3, then I will go to router 4, and then I will go over the link between 4 and 5. Basically, I configure the explicit path right now on my router. And again, I didn't have to signal anything. I made this decision directly on the router 1. If you think about it, the TILFA is actually internal implementation of segment routing traffic engineering on the router. It's completely the same. Creating the traffic engineering, how to steer the traffic over the network. So let's look at a little bit more on segment routing traffic engineering policy, how it works. So we have like 3 important information. First is like head end, the router, which is starting to segment routing traffic engineering policy. Second part is a color. We will talk a little bit more about it once we will touch the services. It's mainly is the thing where we want to somehow identify mainly the SLA type. We want to be sure, which type, is it like best effort traffic, is it for low latency traffic? Basically, I want to have a multiple traffic engineering policies between the head end and the endpoint. And the endpoint is exactly the last part. So locally on the router, I need to have my destination, which is endpoint, and also I need to specify the color. Typically, it will be certain SLA. So then, in this example, I will have like 2 colors. Basically, I will have SRT policy where I have, okay, first one is the green one. It's going to router 4. And second one is a blue one, which is also going to router 4. And for example, the blue one will be low latency and the green one will be the best effort traffic. Now, how I can get this segment routing traffic engineering policy? How I can get this SID list? So for sure, I can configure it statically. Same like with the RSVP, I can go and statically configure what will be my explicit path. I can use BGP to give me this information. I can use a PSAP. I will talk about this too a little bit more later on when we will touch the programmability part. And for sure, I can use the netconf. Netconf CLI is always like the couple how you can do it. So when I will configure a segment routing traffic engineering policy, I have always the candidate path. And later on, I will also show you the CLI very quickly to understand exactly how these candidate paths are working. Typically, what will happen, I will have multiple candidates for the path. And the best one will be installed to my FIP, to my Ceph. And the rest of them will be like a backup. But then what I have also, for each path, I can also configure the SID list with a certain weight. Typically, I will have just one SID list, but what I can do, I can also do weighted ECMP. So basically, I can decide that I will have one segment routing traffic engineering policy where both of them, one candidate path will point to 2 different SID lists, and each of them will have a different weight. It means that I will start to do some ECMP, and this ECMP can be weighted. So in this case, I will have, for example, I will have SRT policy where I want to go first from the router 1 to router 3 and then to router 4. How it looks like in the FIP is that outgoing SID list is 16,003 and then 16,004. You can see something what is like the B SID, the binding SID. This is also something very important, and I will cover it a little bit more later on, because you can imagine that this is like a local label for my segment routing traffic engineering policy. It's my local label which is identifying this segment routing traffic engineering policy. So all this 100% of the traffic which I'm steering over this segment routing traffic engineering policy is going over the node 3 and 4. Now let's say that I want to load balance somehow the traffic over the SRTE. So now I decided that I want to send like 80% of the traffic over the wild part, which is like over the 4, 6, 5, and 4, and then 20% of the traffic over 2, 3, and 4. So I will put the certain weights. You can see the weight 1, weight 4. How it works, the summary of the weights divided by number of the like total number, which means like it will be 1/5 4/5, which means 80% and 20% here in this case. So then when we look at how it looks in the LFIP, originally I have like my local label pointing to my one SID list, 1603, 1604. And now I have also like another SID list, which is like directly 1604. And I'm doing like balancing like 80% of the load I'm sending to the one part directly to the node 6 and 5, and 20% of the load I'm sending to router 2, 3, and then 4. When we look at the basic configuration, just to show you how it works. In this case, I will have explicit configuration, so I'm explicitly configuring to the CLI what I wanted to have for particle policy. So I said, I have a certain color. I decided that it will be color 20 in this case. I'm going to router 4. I can configure my binding SID, like the label which is identifying me as RT policy. We didn't cover why I'm using this. I will cover it in the next slide. But it's it can be dynamic, or I can configure also manually. Then I have a candidate path, and I have a preference. Here, I have 2 paths in my one candidate path, and one is weight 1, and one is 4 for the particular SID list. SID list 1 and SID list 2. SID list 1 is this particular label, so I can put there explicitly, I can identify the node SIDs here, 1602, for example, 3023, which will be another binding label, 1604. Or I can also put the particular loopback IP addresses, and route itself will translate to the labels, to the SIDs. And it's the same example which I had before. So basically, I'm able to use the weights. I'm able to send my 80% of the traffic over the router 6, 5, and 4, and 20% of the traffic over the node 2, 3, and then going to the 4. So with this one, we were able to cover the fast route of the RSVP as well as the traffic steering of the RSVP. Basically, we are able to get rid of the RSVP at all. Please.
Traffic engineering, classical traffic engineering use all announced route from IP to MPLS to DSP.
Yeah.
By traffic engineering, and here you are using this binding.
I will explain binding SID. I will explain right now for binding SID I'm using for. No, it's like initially when you will, first of all, when I will want to send the traffic between, for example, here between the router 1 and 4, I will have some VPN traffic probably there between 1 and 4, and I want to steer the particular traffic to the router 4 to some particular SRTE policy, right? And this particular SRTE policy, you can imagine it as an interface, and to this interface I will steer with a certain criteria. I can have auto-route announce. I will talk about like the way how we can steer with the BGP and so on. But it's not like a tunnel because we don't have any state there. But basically, I'm creating like the interface which is giving me the path over the network. Let me talk about the binding thing in the next slides. So we were able to get rid of the RSVP with this one. And this is also very important, a very important slide, because from the services point of view, everything what we did right now, we are not affecting the service. Basically, my BGP service or LDP service, which is running over top of my segment routing, everything is the same. Because what I need is a transport label. Am I getting the transport label? Okay, I was getting it from the LDP, now I'm getting it from the segment routing. When I have a segment routing traffic engineering policy, I'm getting this label from segment routing traffic engineering policy, right? So for the service, it's a completely independent. Let's look at the intra-domain. First, let's look at the migration here. So in this case, we were running the LDP. The LDP in this case is a blue part. So when we look at the LFIP of each particular routers, so the router 1, 2, 3, 4, everyone was allocating the dynamic label for the router 5, for loopback 1115. And this will be dynamic. So for example, router 3, the outgoing label will be 24320, and the local label will be 24003. It's like it's a dynamic, and it's always like the label swapping here. So what will happen when I will go and when I will configure the segment routing, when I will enable the segment routing, In LFIP, I will allocate this prefix for the particular loopback for the router 1115, router 5 here for the loopback 5. So in case when I'm running the LDP in my network and I configure the segment routing, what will happen from the forwarding point of view? Initially, nothing. You will just have this entry in the LFIP and in your Ceph. Because by default, when I'm configure LDP and segment routing, the Cisco router will prefer the LDP. So you can first go, you can configure it there in your network. You are still forwarding based on the LDP. When you are sure that your segment routing works, you just go and you will configure SR prefer. And that moment on the source router, basically where you are imposing the service, where you are starting the service, you will start to use the segment routing. So you can very smoothly go and you will very smoothly start to configure the segment routing in your network. You can verify that the segment routing is working and then go and start to prefer the segment routing as a forwarding. Basically use the labels which are exchanged through the segment routing. So then when you want to have certain coexistence, you just go and configure under each IGP domain. Again, depends which one you are using. You will just configure the SR prefer. Now, how to do the interworking between LDP and the segment routing. When I want to go from the LDP to SR, it's actually very easy. Let's say that I have router 1, 2, and 3 are LDP only. And then I have a 3, 4, 5 are just SR. And they are inside one IGP domain. So what will happen here is that in this case, I need to, inside the LFIP on the router 3, I need to merge the informations which I have between LDP and the segment routing. Because I have local label for the router 5, but I don't have outgoing label for router 5 in the LDP. So what will happen, I will take my segment routing label, the 1605, and I will use it as an outgoing label. Because again, it's just a label. I just got this label from the different control plane. I don't care. I can do it. So basically, I'm able to merge these informations so it means from LDP to segment routing, it's very simple to go from the left to right. From the opposite one, because I don't have anyone to allocate me the label, because what we discussed, the segment routing, you as an operator, you are the responsible to configure the prefix it, right? So you have to do it by yourself. So again, when I have right now the network, LDP network, which is on the right side, I want to be sure that someone will basically do this configuration or will this advertisement for me. I'm using something what we call the mapping server. The mapping server can be local configuration on the for example, router 3. So basically, I'm here saying that a particular router 5 will use for example, the prefix it 1. So it will be, in this case, the configuration for the router 5. So when I'm going there, I'm able to again merge these two informations between segment routing and LDP, and at the same time, I'm allocating the segment routing label locally on the router 3. Now, the binding SID. Why we are using the binding SID? Why we need to have the local label for segment routing traffic engineering policy? Why to do it? So there are two things why to use this one. One is the stitching. So this feature can be very interesting, for example, for the migration from the RSVP to segment routing traffic engineering, or when I have multiple traffic engineering policies and I want to stitch them together. This is something what I cannot do with the RSVP. When I will have RSVP channel and I want to stitch two RSVP tunnels together, what I have to do? I have to terminate, do IP lookup, and again send it to another RSVP channel. Here, in this case, because I have a binding SID, I can, for example, blue SRT policy is defined. I want to go to router 3, then I want to go to router 4, and then I want to be sure that I will stitch with the SRT, which is a red one. So what I will impose there is the binding SID of the red SRT policy, so which is like 30,410. So first I will go to router 3, I will go to router 4, and because there is like top label then will be 30,410, I will automatically steer to the red traffic engineering policy. And again, I can do the same from the red to the green. So you can imagine that for you, it's like a local identification for the SRT policy. When I will receive any traffic where the top label is the binding SID of some traffic engineering policy, I will just steer to this traffic engineering policy. So I'm using it for the stitching. So this one can be used for For the migration from the RSVP to SRTE, it can be used as an intra-domain feature, but you can also use it over the multiple IGP domains. Because in this case, when there will be like one IGP domain between router 1 and 4, there will be another IGP domain between 4 and 7, and another between 7 and 10. It can be actually a very nice way how you can stitch the traffic engineering policy without knowing another topology, without doing any redistribution and so on. So when we look at like the network design, so first we have because we have a multiple IGP domains. The most interesting one is the simple one when I have access, core, and access. So I'm showing here like two pictures because we know that over the time the access domain can a little grow. Basically, I'm able to very often merge the access and aggregation domain together because of better CPU on the routers. I have a better hardware, so I'm able to accommodate more routes. At the same time, we also know that some of the customers are preferring to extend the core. So basically, I'm able to go with the core over my aggregation and keep the access small. From the technical point of view, when you look at the design, it's pretty much similar here. So now let's go to the inter-domain use case, and let's a little remind how it works with the unified MPLS. So what I have to do with the unified MPLS? In this case, I have an access domain, the orange one on the left side as well as on the right side, and I have some core in the middle. And I'm using the LDP in all three IGP domains, and I'm using the BGP-LU over top. So when I will look at the label stack, which I need to impose on a router 1, A1, I need to impose my local LDP label, which will be for PE2 or PE3, and then BGP-LU label, which I will receive from the inline route reflector on a PE3 and PE2. So basically, I will have two transport labels, then I will have typical service label, and some original packet, right? When I will go over my access domain, again, the last router which is connected to PE2, PE3 will do the PHP of the LDP label. So top label will be the LU label of the A6. Again, router 2 and 3 will impose the LDP label over the core to router 4 and 5, and so on. So this is like the BGP-LU. And I need to have a BGP-LU signaling from from A6, 4, 5. Typically, I will have a route reflector in the core. Again, 2, 3, and everyone is doing the next hop self. So basically, it's like hop by hop, the BGP-LU. So what I can do, like the first one, when I want to introduce the segment routing, I can just go and I can keep my BGP-LU. I can configure the segment routing under my IGP, which I have inside the access domain, and I can get all the benefits of, for example, the TIFA locally in this IGP domain, and I'm still running the BGP-LU on the top. So basically, this can be like the first step. I want to introduce the segment routing. I have a hardware. I have a software which is capable to do it in my one access domain. So I just go there and I can configure it. It's very simple. But then let's imagine that I have one more very cool feature in segment routing, something what we call the anycast SID. So basically, the anycast SID in this case is, imagine that I have a router 4 and 5, and I want them to be represented by one prefix SID. Then it becomes anycast. It's same like an IP. I will configure the same loopback on both of them. It's anycast. So here I have a same loopback and also same SID. So both of them are, for example, advertising 16,100. So what will happen when a router 1 wants to send something over these two nodes? They'll just do, for example, here in this case, we'll do the ECMP over the both, over the 4 and 5. So I don't need to send first to 4 and 7 and then second part to 5. Basically, I'm representing 4 and 5 as a one node from the transport point of view. The beauty of this one is that then I have a redundancy because when one of them goes down, my IGP will get this information, and I will just, for example, router 4 goes down, so I will start to send it just to router 5. So then when I will use this anycast SID here, I'm able to completely disable the BGP-LU, because what I will have right now is I will enable the segment routing inside each IGP domain, and I will use also the segment routing traffic engineering for inter-domain LSP. So basically, we will talk about the controller, how I will be able to get all this information to go from the left to right inside all the network. But in this case, when I have right now segment routing completely everywhere in each IGP domain, I'm able to use the feature of the traffic inject not for fast reroute, not for traffic steering, but also for interdomain LSP. So in this case, the router 1 will go and impose the anycast SID of the router 2.3, anycast SID of the 4.5, and the destination A6. And all of them are basically the segment routing SIDs. 2.3 are defined as an anycast. 4.5 are also defined as an anycast. And I'm basically getting the TI-LFA fast convergence end-to-end in each particular IGP domain independently. Here you can see that I have another component, which I call segment routing path computation element. Because we all the time said, okay, I will impose certain amount of the labels, I will create the label stack, the SID list, and so on. Typically, you will not want to do it like manually, right? You will not want to go and explicitly configure the path that when from the A1 I want to go to A6, I have to go over the 2.3, 4.5, and then the destination. You will want to have someone else to give you this information. And for this one, we are using something what we call segment routing path computation element here. You can also see the orange link here for the BGP. We are using the BGP-LS, BGP link state, to basically get the network topology from the network. So for the controller, I need to be sure that the controller will have the information about the network topology. So when I will request the path, the controller will be able to provide this path to me. The BGP-LS is a standard protocol which is used for basically getting this network topology from the network. So in this case, the PE routers are running the BGP-LS to the route reflector because again it's a BGP, so I can use the route reflector, or it can peer directly with the SRPCE. It depends on the design. Let's say this is a design where I want to scale, and then I have a SRPCE, for example, in each access domain, and I'm able to provide the path to the network. So when we do like very quick comparison of the SRTE for interdomain LSP and the BGP-LU. So when I will use the SRTE with anycast SID, I can add TI-LFA is basically only one mechanism which is doing the fast reroute. And this fast reroute will be done for any node failure, link failure, also of ABR failure. In our previous picture it was PE node, was basically ABR. In case of the BGP-LU, I need to have BGP pick for fast reroute. But at the same time, with the BGP-LU, when I will have node failure of the ABR, I will never ever get convergence time up to 50 milliseconds, because I always need to first let IGP converge, then I can do the FRR with the PGP pick. So with the BGP-LU, I will have a good convergence time, maybe with the link failure, and in node failure, except the ABR there. Then very nice part is that when I will have a controller like the PCE, we discussed that I will be getting this path. I will get this path, this SID list, just in case when I will request it. So when they will be serviced between A1 and A6 from the previous picture, this time I will request to get this path. When there will be additional router, let's say A5, and A1 will not have any service between A1 and A5, I will not request any path, so it means I don't need to program this path to my hardware. And hardware is the expensive part, mainly in the access, right? So you want to save the hardware resources. And this is like very easy way how you are really programming to the hardware the informations which you really need to have there. With the BGP-LU, you can do it, but it's much more difficult because typically you will use the different route targets and you will use the filtering, the routes, and so on. So this is definitely something what is more difficult. And again, we are back in the same segment routing principles. You know, segment routing is a source routing. So I'm just going on my access device. When I want to do any decision how I will go over my network, I will program this information just on the source router. I don't need to go on PE23, PE45, A6. Basically, I'm doing this decision locally on the access router. So I need to program just one device in the network. So with this one, when we look at for SRT policy for interdomain LSP, we are able to get rid of the BGP-LU. So we have anycast SID, we have end-to-end TI-LFA. This is like the most important part. And let's talk a little bit more about the PCE, because we started to discuss that I'm getting the SID list from the PCE, and let's see some of the details. So when we look at the segment routing traffic engineering, the PCE, which we are running as on the top of the iOS XR as a process. So basically, when you will take any iOS XR router, you can run the PCE controller on the top of the router. Typically, we are using the virtual XR 9000V as a PCE controller there. First, I need to get the topology. So I'm using typically BGPLS. It can be also part of the IGP, but typically BGPLS will be the main protocol, how to get the information about the network topology. And then I'm able to compute the path. Again, I will have certain criteria how I will compute the path. I will compute the shortest path over the multiple IGP domains. I can compute disjoint path. I can compute the low latency path, and so on. We will talk a little bit more about this one. And then it's a important interface is how I will deploy this information to the network. Typically, I'm using path computation element protocol, but I can also use the BGP. So again, BGPLS is the standard protocol. It's something what is on the market quite a long time. So most of the routers are supporting the BGPLS, and nothing extra. I'm just take the network topology which I have inside the IGP, and I will introduce it over the BGPLS. Now, nice part of the PSEP, path computation element protocol, two paths, PCC, which is client. This is something that is running typically on the access node or on the PE, and then PCE, which is the compute element. This is like the SRPC, what we just discussed, which can be like the virtual router. This is computing the path. The nice part is that it's typically it's a stateful. So it means that when you will request the path, you will receive the path from the controller, and then something will happen in the network. Imagine that, for example, you go and you decided to change the node sets of your ABR routers. When you will do this, again, through the BGPLS, the controller will get this information that there is a change in the network and will automatically update the existing policy which already provides to you. Because he knows that you requested this path before, and he needs to keep you all the time up to date. But when you think about it, when you will think about like, when you need SRPCE to give you the new information, when any link failure happen, you don't need any new information. The SID list will not be changed because your next label is your ABR. When any node failure will happen, you don't need any new information from SRPCE. When you are using any cast set, when one of your ABR goes down, you don't need any information from the SRPCE, right? So in the end of the day, most of the time, you will get path, and you don't need to change the SID list. So you don't rely on any controller like that. You need to have like up to 1 second, 2 seconds, like a response from the controller. You will just get SID list once, and then all the time you are using it, you will program it to the hardware. If you want to have a fast convergence, you will use again the TI-LFA, but you don't need to react with the controller every minute, for example. So then I said that we are also using, except the PSEP, we can also use the BGP. There is a new draft for the BGP, new address family, where basically BGP can also signal this information from the controller. So you will get your SID list from the controller directly through the BGP. Another important component of the provisioning the service is the NSO. This part is a little separate. I wanted to just touch the programmability because we are using this tool for really provisioning the service. It's not about like programming the path. Very often I'm getting the question, okay, so except as RPC, can I just use the NSO and use it as a tool how to program the SID list statically on the router? Yes, for sure, I can do it. But now we are back in the previous discussion when we talk about that SRPC is basically holding for me the state. So when something will happen in the network, then I somehow need to bring this information to NSO, and me as operator, I have to go and I have to probably reconfigure the path. So here in this use case, I'm holding the NSO just for the service provisioning. From the service point of view, there is network, and I'm able to go from the node A1 to A6, and I don't care about it. I know that the transport self with the controller, with the SRPC, will take care of this. And I'm just provisioning the services. So what is the typical flow here? So you will go on the access router, you will provision the service. You can do it from the NSO, or for sure you can go and do it through the CLI. Then, because you are requesting, the service will get certain next hop, so the access router will ask SRPCE through the PSEP, hey, give me the path. And now I will have certain criteria. I can say, hey, give me the path, best effort path, shortest path based on the IGP. Give me low latency path. Give me the disjoint path. Give me the path which will follow, for example, blue links, like certain affinities and so on. So this is like the way how then basically access router is doing, like, or service is doing the decision which path you will use inside the network. So when we look back to this picture, I provision the service on A1, respectively on A6 as well, most probably. And then A1 asks the SRPCE over the PSEP, hey, give me the path. So all this SID list, what you see here in the network, like, going on the Anycast 2.3, 4.5, and then the destination A6 is basically from the SRPC. Typically, you will not do it manually. Now let's touch the part why the BGP is so important for all this segment routing and segment routing traffic engineering. There is something what we call on-demand next hop. And you will see, like on the next slide, how basically I'm able to really tie, the service together with this underlay transport which we just discussed. So let's imagine that I have an example where the router 21 is signaling over the BGP. It's L3 VPN service. It's signaling over the BGP certain route, 111.21/32. Just example. 22. Will signal this path to the local route reflector, but because I decided that this particular route for me is, for example, some low latency traffic or best effort traffic, I want to put some SLA type. I want to say this particular route for me has a certain value. So I will use the extended community value inside the BGP to put this information together with the route. It's a standard extended community value. We don't need to have any extension inside the BGP. So I will signal this extended community to the route reflector. Route reflector will send it to the remote PE, and the remote PE will basically request the path. And based on this extended community, will say, okay, I want low latency path, I want best effort path, or I want to minimize TE metrics, like for example in this example. Now what will happen on the router, on the remote router 3? I receive this particular route, 121/32, with the next hop PE2, PE22. I will get certain BGP label for the service, obviously, and then I have this community. I will request the SRTE policy. So basically, I will get the SID list from the SRPC based on the certain criteria, and I will get again this binding label for this SRTE policy. This binding label is, for example, 30,022, dynamically allocated in this case. I will take also this binding label, and I will also program it in the FIP. We also discussed that basically when I will program the SRTE policy, I will go to the FIP, and it will be like my local label. But I will also take this binding label, and I will also use it as my next hop for the BGP. So basically, I said that for this particular prefix, I want to use the next hop 30,022, and this 30,022 is basically pointing to SRTE policy, which is going through the network. What it means is that I have a granularity that I can, for each particular prefix, I can use, for example, compute a different SRTE policy. I'm not saying that you will do it, but you have a granularity. For each VRF, I can have different prefixes, where each prefix will have a different SLA type, and for each SLA type, I'm able to program the specific SRTE policy. Now, we discuss, okay, I can have like a best effort path, I can have a like low latency path, but how I will get something like low latency path? Best effort path is easy. Shortest IGP metrics, I can go over the network. We know that we have like IGP domains. Each IGP domain will give me this topology together with metric. There is a controller which is calculating the shortest path. This is easy. But now let's talk about like the low latency, because for the low latency, first I need to know what is the low latency link. I don't want to use it as a static information in the network. We have something what we call the performance monitoring. The performance monitoring is the local behavior, again, of the router. Each router is using the MPLS OEM packets to check the latency for each link. I can do it one way or two way. When I want to have a two-way, I need to have a time synchronization in the network for the latency. But basically, I'm sending the probes, and I'm able to measure the latency for each particular link. And now, important part is how I will get this information from the network. Because in past, we were using SNMP, NetFlow, you can use another collectors, whatever it will be, but it will be always very difficult. We will use all the standards which we have for the IGP. First implementation is in ISIS, but we'll also advertise it as a part of the ISIS TLV. So you don't need to have another interface. You don't need to have anything else. You're just using your standard IGP protocol to also advertise you another metric, which will be right now the low latency metric. And it will be changing dynamically. It will be like over the time, over the day, it will change because, for example, when you will have a microwave in your IGP domain, you will see that the microwave is changing the latency. Basically, you will change the metric, and again, you will advertise it inside the IGP domain. So then, again, you will take the BGPLS, and BGPLS is providing the metrics for the shortest path, but now it will also provide the low latency metrics, right? So in this case, I'm able to calculate the low latency path, again, without any additional interface. So I can ask directly the PCE to give me the low latency path, which will be a real low latency path from the network. And again, it can be end-to-end. There is one more part which is actually very important for this programmability, and it's Flex Algo. Flex Algo is something which is like complement to SRTE policy, and it's bringing you something like multi-topology view on each particular router. So it means that I can, for you, it can be, you can look at this one as you are getting the option to specify the algorithm, how you will calculate the shortest path. Let's say that algorithm 0, which is well known in IGP, this is the shortest path, will calculate the shortest path based on all the links which are in the IGP based on the metrics, right? And then you will say, okay, but my criteria is to calculate the shortest path based on the certain affinity, based on the blue links or based on the green links, red links, and so on. One of the criteria can be calculate me the path based on the low latency informations. So this is another option what you can do here with the Flex Algo. So then when we look at it like how it looks really in the network is that I can have like the multiplane. So here for example I specify I have like a green part which is minimize me IGP metrics, and the green part and the red part which is minimize me the delay. So in case when I'm on the router, in this case 0, I want to send the traffic to router 9. Again, based on the BGP extended community which I will receive from the service, I will make a decision if I will forward based on the IGP which is specifying the minimized IGP metric, or I want to forward based on the IGP which is specifying to minimize the delay. So let's take the example. Let's take the network where I have again access, core access, simple one. I'm using one SRPCE. Again, I can have distributed SRPC. It's just the example. And each IGP domain has the black links, which are like 100G links, but they are like best effort links, let's say. And then I have red links, which are super fast. They have low latency, but they are super expensive. And you want to be sure that you will just use the red links just for the traffic, which is very important for you, basically for some VIP traffic, or you are charging your customer extra for using these links. So again, I'm creating the L3 VPN service, VPN v4 in this case, and I'm using the BGP community to signal this information. So I'm signaling the information, okay, this is a best effort traffic. A1 will calculate the path, will ask the SRPC, hey, give me the path for the best effort traffic. So I will use the algorithm 0, I will use the set of the ABR1, I will use the set of ABR2, and I will use the destination. And now is a very nice part. Each of the flex algo has its own set of the prefix sets. So in this case, when I will impose the algorithm 1 ABR1 set, it means that even router A3 knows how to forward based on this algorithm, because also router A3 has the multi-topology view and understand based on which algo, based on which topology he should forward over the network. So I don't need to have any additional labels to specify hop by hop over the IGP domain. I'm just using the separate prefix set for each particular flex algo inside the IGP domain. So then when I will have a second example, when I will signal that I want to have a low latency path, again, A1 will ask the PC to give me the sets for the low latency path. And you will see that the number of the labels is completely same. It's also going to ABR1, it's also going to ABR2, it's also going to A6, but the prefixes will be different. This prefixes will be, for example, from flex algo 128, which was defined for the low latency. So with this one, I'm going also over the limitations which I can have in the hardware, because in the hardware, for sure, I will not have options to impose the unlimited number of the labels, right? So with this one, I'm able to divide the network on the multiple parts. In each part, I'm able to say, okay, this will be my shortest path, this will be my low latency path, this will be like my computation based on the affinity, whatever. Now let's compare how looks the MPLS and how looks the SRv6, basically segment routing with IPv6 data plane. As I promised, there are no labels anymore. There is no something like, it's not like LDPv6. I'm not using the MPLS labels at all. Basically, I'm using IPv6 address as a set, as a segment, which before I was using MPLS label was my node set, now it's a IPv6 address. I have this whole 128 bits where I can encode a lot of information. Basically, the prefix set in with SRv6, we are dividing on the multiple parts. One part is a locator, and second part is the function. So you can imagine that all the locator part is like the prefix, which is basically behind certain routers. And then the function, for me, is specifying if it's, for example, a certain VPN or if it's cross-connect. Basically, I can really put there a lot of information which I can carry directly with the packet itself. So then how it works, because I said it's basically IPv6, so there is no MPLS at all. So when I have like the network, right now I will forward from A1 from 1 to 4 on the right side. So I have a header, IPv6 header, where I have a source address 2001:11, which is identifying router 1. I will have a destination address, which is 2001:4 and E100. This E100, as I explained, is a function which here on the router 4 explaining that it's basically the termination in the VRF 100. It's a local function on the router 4. But the forwarding information which I'm using in the whole network is hold the prefix 2001:4/4864, whatever it will be the prefix there. So basically I'm going over the network, I'm using the IPv6 routing to go from the router 1 to router 4, and then locally on the router 4, I'm looking to the prefix set, to the particular destination address, looking to the function part, and this function part locally on router 4 is defined as terminating in the particular VRF, which is VRF 100. There is one more thing inside for SRv6 is I want to also have an ability for the steering. So basically what we had before with the MPLS, we were like stacking the labels. We had SRT policy, we were stacking the labels. Here, what I have, I'm imposing another SRH header when I have also the segment list, which are also the particular 128 bits, node sets or identification of the links and so on. So here, example, I want to forward the traffic to router 1 to 4. Again, I want to terminate there on the router 4, but I want to be sure that I will use the link between router 3 and the 5. So how will look the packet? Originally, what I will impose on the router 1, I will impose the destination address, the address of the router 3. But when you look at on the function part of the destination address is a C35. And I define this C35 as a function for the cross-connect between link between 3 and 5. But at the same time, what I will do, I will look at to segment routing header, and I will look at for the next segment list. And my next segment list is again 2001 for E100, like I had before in my previous example. I will put this as a new destination IPv6 address to IPv6 header, and for sure I can also delete this SRH header because I don't need it anymore, because it was the last important information which I had there. And then I'm sending the packet over the network. So when the packet will arrive on the router 4, I'm getting a completely same packet I had before. I will look at my function part, and my function part is again E100. E100 here means terminate in VRF 100 like I had before. So this one was a very quick taste of the SRv6, where we are going. With the BGP services, I will right now I will go more on the BGP part because I want to explain why we are focusing so much on the BGP, and you will understand why we are going with the BGP across whole the network. And I will talk more about mainly EVPN and how EVPN is an important complement for overall design in service provider network. In particular, we know that basically most of the service provider networks needs to integrate something called CO, SPDC, DC, and so on. So when you look at this picture, on this picture we are showing that the current design. When you look at to the one, you can look at to the access. We are always using, most of the time we are using the MPLS. So with the segment routing, we can really simplify the network, which we discuss right now. But we have a different part for the services. For the services, typically for L2 VPN, we are using the VPLS, or for point-to-point services, we are using the traditional pseudowires. For L3 VPN, we are using BGP, VPN v4, VPN v6. But then we have a completely different set of the protocols in the DC, because there we were using the different data plane. Typically, it's a VXLAN, it can be fabric pod, it can be Trill, and for the services, it's the same. It can be for the transport, it's also the different. When we go on the DCI is then very difficult part, because DCI needs to interconnect these completely different worlds. It's something that you are requesting different data plane, you are expecting different control plane, you are requesting the different scale from the MAC address point of view and different scale from the IP prefixes point of view. So basically you want to have something that will scale from any perspective, right? Number of bridge domains, number of the VRFs, everything. When you look at, and when you will be able to get the one data plane everywhere, so basically you will be able to get rid of the first part that you don't need to do the stitching on the data plane level. So basically you can also implement SRTE, MPLS segment routing inside your DC. And then you want to find a way how to do the common BGP and use all this ODN for the traffic steering, like really end-to-end, what we discussed in the previous example. So when we look at the current limitation, mainly in the core, when I compare it with the VPLS, this one is comparing when, for example, C1 is connected to PE1 and PE2, and I cannot do the multi-homing. Why I cannot do the multi-homing here? Because VPLS has a technical limitation. When CE1 will send the broadcast, unknown unicast, and multicast traffic to PE1, PE1 will flood this broadcast traffic over all the core. PE2 will receive this traffic and will send it back to the access. So I will have a local loop, right? The second one, even if I will go over this limitation, when PE1 will send the broadcast, unknown unicast, and multicast traffic to PE3 and PE4, I will have a duplicity, because PE3 will forward it to the access, PE4 will forward it to the access. Then last one, when I will have a multiple flows, which will be going over the PE1 as well as PE2. On the PE3, I will have a problem that one flow will be received from PE1, and the second flow will be received from PE2. So with VPLS, I will be always rewriting the MAC address table. So I will have a MAC address flip-flopping. So all these things we want to fix with the EVPN. So when you look at the EVPN, how we can really deploy the EVPN is basically we are able to cover all the existing services. I'm very explicitly saying here, we don't have an intention to go and replace the traditional L3 VPN service like VPN v4, VPN v6, because there is basically no technical benefit to do it. You can do it with EVPN. There are all possible mechanisms how to do it. But again, the control plane is the BGP. We don't care about like different address family. That's the very important part. The key advantage is we want to bring something similar like L3 VPN, because L3 VPN over the time proved that it's one of the best technology for the L3 VPN services, and we want to bring something similar to the L2. So we want to go from the MAC bridging to MAC routing, something what we have today in the L3 VPN. We have something with EVPN what is completely independent on the data plane. So I was talking about MPLS data plane and how you can use the EVPN with segment routing MPLS transport in your, for example, even in your data center. But at the same time, if you want to keep the VXLAN or something else, you can do it. It's independent. In our case, most of the time we are going with the MPLS. So now when I will compare these two, it's really for us when you look at the configuration, and I had like a previous session was talking a lot about like how exactly looks the EVPN configuration. You don't want to go and touch your existing L3 VPN services. You want to more find a way how you can use the BGP as a complement to the existing one. So basically you are bringing the new address family for the EVPN. You are able to do L2 stretch. You are able to combine L2 together with L3. We will go over it. But because it's a BGP, it can be very easy to stitch traditional L3 VPN services together with the EVPN, and we will also cover this part. To me, EVPN has two flavors. One is like that you can first go and you can replace any existing solution, because you are with the EVPN, you are mainly trying to simplify your Ethernet access. Today, Ethernet access, you can use multi-chassis LACP when you want to do any kind of the multi-homing, but it's definitely not any active, it's per VLAN active. You need to use the ICCP between two devices to synchronize the state. Or you will use the hierarchical VPLS, so you will have active backup pseudo-wire. So you cannot have like active access, again, because VPLS has a certain limitation. So then you can also replace like the targeted LDP for any type of the VPLS pseudo-wires, and you don't need a BGP auto-discovery for this one, because you are using the BGP as a signaling for everything. Another flavor of the EVPN is use the EVPN as a standard protocol for multi-chassis. When you look at today, you can use the VPC, VSS, all the releases of the cluster, but you can replace all this with the EVPN as a one control plane, which will synchronize the MAC address as well as the ARP for you, and we will go over some of the details. When we compare the very high-level picture, when we compare the L3 VPN BGP service with BGP EVPN, you know, what is the difference from the data plane point of view? From the data plane point of view, there is no difference. Again, I need my transport label, I need my VC label, like my BGP label, and in case of the L3, I'm putting the IP packet there. In case of the EVPN, I'm putting all the frame as a data, original data. Who wants to know more about EVPN when you will want to go and when you will want to check the standards? Most important standard is RFC 7432. We are dividing to two parts. One is the multi-point, which is the most important. Multi-point with the multi-home all active access is the one which is the most important one. Then we have integration with the IRB. I will talk about it a little bit more. It's also a very important draft. And then we have also the point-to-point services for the EVPN VPWS. So basic concept. Let me go over these four important parts, or maybe three important parts. First is that you need to have always a certain instance. You have instance for the EVPN you have today. So it's something when we will compare it with the L3 world, you need to have a VRF. In L2 world, you have a bridge domain. You are using, for example, as an outgoing interface today, you have for the VPLS, you have a VFI. With the EVPN, you have EVI. When you look at from the configuration point of view, there is not too much changes in terms of the L2 VPN bridge domain configuration. Now, very important is the Ethernet segment. Ethernet segment is something what tells me I'm multi-homing same broadcast domain. So basically here, between PE1 and PE2, I want to be sure that they will know that they are in the same broadcast domain, because they need to take care that they will not create a loop, what we discussed. When I will send the broadcast, anonymous and multicast traffic from the CE2 to PE1, I want to be sure when I will send it back to the PE2 will not send it to the access, right? Because it's a BGP, I have a different route types. This is like 5 most important route types. We have a little more for the multicast, but with this one, you will understand what basically, how is the basic concept of the EVPN and how exactly works the control plane. And each route type has a for sure certain extended community, but this is something we don't need to cover here. The nice part of the EVPN is that you can always imagine that doesn't matter if we are looking at the configuration on the leaf spine or we are using the PE. Basically, everyone can use home picture. If you like more like a data center and configuring EVPN in the data center, okay, look at it right now on the left part. If you want to stay in your service provider core and access, look at on the right side. But configuration-wise, the principles and everything is completely same. There is no difference. And it's also another reason why it makes sense to think about EVPN really end-to-end, because you will have your same configuration template in your CO, in your DC, next generation CO, whatever it will be, and also in your access and in your core. So then, what will happen initially when I will enable the EVPN? When I will enable the EVPN, I will get certain frame. For example, in this case, C1 will send the frame which will arrive on the L1, on the leaf 1. So basically, I will have data plane learning. From this data plane learning, I will take this MAC address, I will use the BGP, and I will advertise this MAC address everywhere inside over the EVPN. So in this case, it's a completely same like IP route, right? I learned the IP route, and I was able to advertise it over my EVPN domain. So next one is important is the Ethernet segment. We discussed that I need to be sure that L1 and L2, same for L3 and 4, they know that they are sharing the same Ethernet segment. It's a 10 bytes value, which as operator, I'm supposed to configure on both of them. So when they will start the BGP control plane, they are able to negotiate who will be the one who will not forward basically the packet back to the access when it will receive from the neighbor. And also for the remote nodes, when I will receive the packet or broadcast, anonymous and multicast traffic from the remote, when and who will forward it to the access, and I will show you the details. So I have a multiple modes how I can make the access, the Ethernet access to, in this case, PE1, PE2. The first one, most important, is all active per flow, where basically I'm configuring the bundle on the CE1. So from CE1 point of view, the P1 and PE2, they look like one device. So there's like one virtual device. This is the same like you will configure the VPC or you will configure VSS cluster, whatever. So here I'm really doing the balancing inside of each VLAN based on the flow. I'm doing the hashing on the bundle. Then another option is to use the single active. This is a use case where I, for example, want to enforce certain policy like QoS and so on. So I want to be sure that one link will be active, second link will be the standby. In this case, I cannot configure the bundle on the CE2. Why? Because I cannot be transparent. The CE2 has to decide, which link is the active. When I will configure the bundle, there is no way to decide that, one link is active and second link is a standby. So typically, you will have like a two separate like uplink interfaces. It's more like the use case when you want to really replace and have a similar behavior like with the multi-chassis LACP, or you had, for example, with the VRRP or with the HSRP. The last mode, which we will introduce this year, is something what we call port active. It's in case when you are using the LACP between the CE3, PE1, PE2, and again, you have a transparent channel here. The PE1 will, for example, in this case, will say, okay, I want to be sure that just PE2 is active. So from LACP point of view, we'll put the interface to the error mode. So it means that the CE3 will stop to use this interface as well. So you will have really like single active with the bundle configuration. So hold the port between PE1 and CSP looks like unavailable at the moment. So with this one, you can also enforce the QoS, for example, on the PE2 in this case. So what I have to do when I want to be sure that I will receive the broadcast, unknown unicast, and multicast traffic on the L3 and L4. Because when I will send the broadcast traffic from the C1 to L1, the C1 will flood this information everywhere. So basically, the traffic will arrive on L3 and L4. And I need to be sure that just one of them will send it to the access. Again, L3 and L4, they will use the information about the same Ethernet segment, and they will agree who will be DF. So just only one will forward the bump traffic to the access. Now there is a different question. When I will have a bump traffic arriving on the L1, and now the L1 will flood it and will send it to L2, how am I sure that the L2 will not send it back to the access? What I'm doing here is I'm imposing one more label. We call this label BAM label. The question now, when the BAM label, then the BAM label is for this particular Ethernet segment. When the L2 will receive this BAM label, we'll look at the BAM and say, okay, I cannot forward this BAM traffic to the I cannot forward this traffic to the access. So basically, this split horizon, which is like enforcing me to drop this packet on the L2, will protect me to create the loop on the L2. Now the question is, when I know that on the L1, I will send the traffic to L2, and the L2 will drop the packet, why I'm sending the traffic there? The answer is so simple, because I can still have a single home device which is just connected to L2, another device in the same bridge domain, and there I need to send this broadcast traffic. So it means that I'm filtering this BAM just for the same Ethernet segment where I'm also receiving the broadcast traffic. So now, one thing which is very important, mainly when we are talking about the data center and the number of the MAC addresses and so on. We want to be sure that there will be fast convergence when, for example, some link goes down. What typically works with the BGP, so for each particular route, you will advertise the particular route to the neighbors. Now imagine that under the C1, which is compute, will be 1,000 virtual machines. So I have 1,000 MAC addresses. So theoretically, it would be like 1,000 updates. When then the link between L1 and C1 goes down, I have to withdraw 1,000 routes, which will take some time to control plane to do it. So what I'm using here, I'm using the way how I can do the mass withdrawal. I have a basic function that each MAC address is pointing to the remote leaf, but is also pointing to the remote Ethernet segment. So when particular Ethernet segment, for example, in this case, the link, which is from L1 to C1, which has, for example, ESI1, goes down, the L1 will send one route withdraw for this particular ESI. And everyone knows that any MAC address behind this ESI must be withdraw. So only one route withdraw, and I'm able to completely clean the MAC address table across whole the network. So then, one last thing, which is there for the broadcast, when I will receive the BAM traffic, I have to always replicate it everywhere. And again, depends on my underlay infrastructure, if I want to use the underlay multicast, or in our case, by default, we are using the ingress replication. So basically, on the ingress, L1 will replicate the packets to L2, L3, and L4. Now the important part is the aliasing. Aliasing is something what we know in the L3 VPN as a BGP multipath. So basically, I will learn right now the MAC address on L1. When I will learn the MAC address on the L1, I will advertise it everywhere. But I also know that this Ethernet segment, this MAC address, is also connected over L2. So I will also advertise, because everyone in this case knows that this MAC address is connected to L1, but over particular Ethernet segment, right? So everyone can also make the entry for, leaf 2, because they also know that this same Ethernet segment is connected to the leaf 2. Only one thing what they need to know is the additional label. So it means the label which they will use to forward when they will send it to L2. So for this one, we are using the route type 1 for the aliasing label. Next one is the make mobility. In data center, what can happen is that it will not typically be in your SP access or in your SP core that you would be like moving with your CE. The CE will be quite stable. But in the data center, you will take the VM and you will move it across the data center. And you want to be sure that you will update this information as soon as possible. So in this case, when I have a VM connected first to the leaf 1, I will move it behind the leaf 3. Immediately when leaf 3 will get the data plane frame, so basically will learn the MAC address on the interface connected to the leaf 3, will advertise the new MAC address. But what we'll do will increase the sequence number in the update. So it means that this higher sequence number, everyone will go and will immediately rewrite this information, will not wait for any withdrawal from the L1. So basically, with this sequence number, the route will get immediately the precedence. This is very fast in case of the mobility. Now, I promise that I will also touch the part how to integrate L2 and L3 together. What I can do here is I want to be sure that my gateway is as close as possible to my VMs. So I want to be sure that basically my L3 default gateway will be probably on the leaf, because when it will be on the leaf, I can do the optimal decision in case of the forwarding. Because when I will have L3 on my leaf, when I will want to do any inter-subnet routing, I can make this decision directly there, right? So for this one, we are using the distributed Anycast IRB, where basically I will go and I will configure the same BVI interface with the same IP address, same MAC address on all the leaves where I want to have a particular subnet. Now what will happen? We will advertise this MAC address. So I know when I'm advertising the MAC address over the route type 2, I'm able to synchronize my MAC address table. But route type 2 has the option to advertise also the host address. So basically, I'm able to advertise the VM MAC address, but I'm also able to advertise the VM IP address. And when I have these two informations, it means that I can also synchronize my ARP information. So here, between the L1 and L2, I will synchronize MAC address, and I will also synchronize the ARP. On the L3, L4, I will also synchronize MAC address and the ARP in the orange and particularly for the red subnet. We are doing actually the same for the multicast. We have also like the same for the IGMP sync, but it's something for this coming in the next releases. So in this case, when L1 want to forward the traffic, so VM, let's say VM, the red one, want to forward the traffic to the orange one, how will be the flow? The packet will reach the L1 or L2, and then L1 will do routing decision and forward it to the L3. I don't need any additional gateway which will do for me the routing between the subnets. So basically, leaf is directly the aware. When I will move the VM from L1 to L2, VM doesn't know about this move. So how I said, the BVI has the same IP address and same MAC address. So when the VM will basically continue with the forwarding to the default gateway, what will change? Nothing, because it's following the same rule. So then, when we look at important part in this one is also like look at how we can interconnect the L3 VPN and the EVPN. I promise that this is also like very, very important because you want to be sure that the basically services will be interconnected together without any issue. So I'm running, in this case, I'm running the traditional L3 VPN service, VPN v4, VPN v6 in my core and access, and I'm running the new EVPN in my data center. So what will happen here is that I don't want to take all my host routes from the data center and send it over the call to the L3 VPN. So basically, I don't want A1 to have all the host route installed in the routing table. Basically, also in the FIP in the LFIP. So what I will do, I will filter the route type 2, which is identifying the host address for me, which we discussed, like that I have a route type 2 for MAC address, optionally IP address, which is host route, which is /32, and I will try to advertise just the prefixes. So for this one, I'm using the route type 5. Route type 5 in the EVPN is really for advertising the prefix. It's just something like very similar to L3 VPN. So what will happen, I will enable this route type 5 on the leaf 1 and leaf 2 in this case, and I will advertise both. The DCI border leaf will be able to store in the forwarding table both